assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question says that carbon monoxide replaces oxygen in oxygenated hemoglobin according to this reaction, where oxygenated hemoglobin reacts with carbon monoxide, so that carbon monoxide is now bound to hemoglobin and free oxygen. It asks us two questions. The first is to use the reactions and the associated equilibrium constants at body temperature to find the equilibrium constant for the reaction below. So these are the equilibrium constants for hemoglobin reacting with oxygen and hemoglobin reacting with carbon monoxide. We need to figure out what the equilibrium constant is for this total reaction. So let's look at the orientation of these reactions and also how the stoichiometry compares to the big reaction up here. In this reaction, Hb plus O2, that's flipped from this reaction. We start with HbO2 and we're forming O2. So if we wanted to flip this equilibrium constant, we would take the inverse of it because this is products over reactants. We need to flip that so it's reactants over products. So to calculate the equilibrium constant for the whole reaction, I'm just going to draw a little arrow. This is now 1 over 1.8. So that's what the equilibrium constant is of the reverse reaction, it's just taking the inverse. For the second reaction, Hb plus CO forms HbCO. That's in the correct orientation. We are going from Hb and CO to forming HbCO, so we're going to keep this reaction equilibrium constant the same. And in terms of stoichiometry, everything is accounted for. There's only one of everything here. There's only one of everything in these little reactions. So now we just need to figure out how to combine these two equilibrium constants to figure out the equilibrium constant of the whole reaction. And that's simply multiplication. You multiply the equilibrium constant of the half reactions to get the equilibrium constant of the full reaction. So that Kc is going to equal 306 times 1 divided by 1.8. That gives us an answer of 1.7 times 10 to the second, or about 170. So this is the equilibrium constant of this full reaction. That's the answer for part A. In B, it says that we should suppose that an air mixture becomes polluted with carbon monoxide at the level of 0.1%. And it says, assuming the air contains 20% oxygen, and that the oxygen and carbon monoxide ratios dissolved in the blood are identical to those of the ratios in air, what is the ratio of HbCO to HbO2 in the bloodstream? It asks us to comment on its toxicity. And we already know that carbon monoxide is toxic. And now we can kind of look at why here. So if this is the equilibrium constant for this reaction, we know the equilibrium constant because we just calculated it here. So Kc is 170. And we know the concentration of O2 and CO from the question. It tells us that it's 20% O2 and 0.1% CO. And if we plug those in, we can simply get this ratio by itself, which is what it asked for. It asked for the ratio of HbCO to HbO2. So let's quickly put all of those numbers in. We said the equilibrium constant is 170. That equals the concentration of HbCO times the concentration of oxygen, and I'm just going to leave the percents as whole numbers, as long as everything is kept in terms of percents. O2 is 20%, so I'm just going to write 20 here. And then on the bottom, we have HbO2, and the concentration of carbon monoxide was 0.1%, so I just put 0.1. Now, if we were to rearrange and solve for this ratio, HbCO over HbO2. And this is done algebraically simply by multiplying 170 by 0.1 and then dividing it by 20 would leave us with this fraction. this equals 0.85. And it might be easier to describe this if we write this as a fraction. This is the same as the fraction 17 over 20. Okay, so that's the ratio of HbCO to HbO2. What does this mean in terms of toxicity? We can think of these numbers, these whole numbers, 17 as 20, as parts of a whole. So in this mixture of HbCO and HbO2, 17 parts of it are HbCO and 20 parts of it are HbO2. And that's kind of staggering. That puts the total number of things at about 37 if you add these two together. If 17 of those 37 are HbCO, that's almost half of all of the parts are HbCO, even though its concentration was only 0.1%, significantly lower than 20% for oxygen. So that's why carbon monoxide is so toxic, because it binds to hemoglobin so much more tightly that only having 0.1% carbon monoxide in the air is able to occupy half of all of the hemoglobin. So that's why it's so toxic.